Hey everybody, today I'm going to talk about some of the material in lab number 7. Remember, you're not required to do the labs, but I'd like to use them to give you a little extra content and go over some code and interpretation stuff in advance of the homework assignments being done. So the first question focuses on doing a components analysis. Remember, one of the key distinctions in the factor analysis section was the difference between a component analysis and a factor analysis. Components try to extract components, and they try to reduce the number of variables that we have to a certain number of dimensions or components. And the way that it tries to do that is by trying to explain all of the variance that is held within the variables. In contrast, a factor analysis is a dimension reduction technique that tries to explain only the variance that is shared among two or more variables. So if something is not shared, it's not going to be part of that factor analysis equation. In general, components analyses are used probably a lot more by mathy type people who are simply interested in a truly exploratory approach, whereas factor analyses are much more common in psychology when we're doing psychometric type work, trying to determine properties of various scales. So the first question asked you to do a components analysis. The idea behind this is I want to compare the components to the factor analysis just to show some of the differences between these approaches. Now, one thing with these data are really highly correlated, so it gives us a number of errors. There's something called an ultra Haywood case. I'll talk about that second. Don't worry too much about that. These just are not great data for factor analysis. The first approach that we're going to talk about is determining how many components or how many factors. I specifically said components here because I wanted to discuss some of the techniques that we use for determining components or factors. They're the same techniques, but we want to be specific to the technique we're using. So this is what's called a scree plot, and this is part of base R. A scree plot is a graph of the eigenvalues. Remember, eigenvalues, what those are, is it's an estimate of how much variability is explained by any one factor. And in general, your first factor will explain the most because it's the first one there. The second factor will explain less than the first factor, often with a big drop off. And then gradually as we go down, we see less and less and less variability being explained. Our goal is to figure out, okay, how many factors are explaining something real and how many of these are just random noise. The term scree is actually a geological term. It has to do with the stuff that falls off a mountain. So if you look at the bottom of a mountain, there's going to be all of these rocks and debris. And what's underneath the scree is the actual mountain. Well, this scree plot is trying to tell us what the mountain or the factors are and what's just the garbage that fell off. So we get a scree plot here. This scree plot is a bit problematic in my eyes in that it shows, okay, this value of 1, and it's got a line there. The reason why it does that is that a popular technique for determining number of dimensions, either components or factors, has traditionally been what's called the Kaiser criteria. The Kaiser criteria is one where we call anything with an eigenvalue of greater than 1 a factor, and we'll talk about why that is problematic. Not a best practice, but you do see it used a great deal. In fact, I just reviewed a paper recently which used that criteria. Another approach is what's called a parallel analysis, and I think this is the one that I would recommend the most. Here's what we have here, and you can see in the code I called for parallel analysis, and then I specified that I want PC, or principal components analysis. If you don't specify this, you'll get a graph with both components and factors. I find that graph to be a little bit busy, so this is a little bit cleaner and easier to look at. So here is my parallel analysis. It's also a scree plot, but it's plotting something a little bit different. Instead of using a criteria of 1, what it does is it's got our data, the one with the X's and the solid line, and simulated data. That is, the parallel analysis procedure creates 5 random variables, just randomly random numbers for 5 variables, and then it does a components analysis on those to show what the components would be if we just had random variables that were not related to each other in any reasonable way. One thing we see to start off with is that the first factor for that dashed line for the simulated data, it also does resample data, but generally these are on top of each other, so there's not much difference there. We get a pattern where we've got the most variance explained by the first factor, and then we're going slowly downhill until we get to the fifth factor. What we generally want to say is, okay, any of our actual data values that are above that line, we're going to say are factors. So the first one, that tells us, yeah, we have at least one factor. This one here, it's a little borderline, but I'm going to be generous and say, okay, that's also a factor. Everything else is down below the line, so none of those are going to be included in our final analysis. What this means is that we have a two-factor solution. We have two factors that were above we would get with random noise, so that's what we're going to run with. So the first step in factor analysis or components analysis, always determining how many dimensions you're going to reduce to. So once we make that determination, generally scree plots with a parallel analysis is the way to go there. Then we are going to move forward and actually extract that number of factors. That means we're going to force the data to fit onto that number of components, that number of factors. All right, so, and the output here will also, will tell you, it says parallel analysis suggests that the number of factors equals NA. That's because we didn't ask it for factors. Number of components would be 2. So this code even interprets that for you. Next, we run the components analysis using PCA. Again, this kind of tells you about kind of the math psych divide here. PCA, the principal command is in base R, but if you want to do a factor analysis rather than a components analysis, that would be in, you'd need a package for that. So a couple of things here. I give the name of the data file. I give the number of factors. I say, okay, we're using 2 factors. And then rotation. Factor rotation is an approach to making your factors more interpretable. If we do an analysis without rotation, what we'll see is that just about everything will load highly on the first factor, because that's going to be the one that explains the most variance. And then we'll just see a trickle of stuff on the other factors. By rotating the factor space, what we're actually doing is we're making it so that we're maximizing the correlations of variables on the factor that they're most associated with, while minimizing their association with the other factors. So it provides an interpretable solution. I would say I would never do a factor analysis without rotation. Varimax is one of the popular approaches. There are a lot of approaches that people will argue about. Generally, they will mostly do the same thing. I think in the psych package, they default to what's called min-res, or a minimum residual approach. You can really justify just about any of these approaches. There's not going to be substantial differences. And if there are substantial differences, it probably means that you don't have a clear factor structure. I like this FA sort command. What that will do is it'll put these in order so that you can kind of see, okay, here are the ones that go with the first component. Here are the ones that go with the second component, and they're ordered in terms of size. So you can see the sorting here. What that's done is it's kind of, it's kind of maximized. Anyway, it's kind of maximized these 3 values on, show that those go with the first component, and then these 2 go with the second component. Useful to try to interpret the factor structure. We foresee the first component has large loadings for death rate, life expectancy for men, and life expectancy for women. The second component, population increase and birth rate. So we see 2 very clear components here. The first one dealing with how often people are dying. The second one, how often people are making the babies. So those are the 2 factors. Again, always useful to try to interpret these in terms of whether things are meaningful or not. We also see, though, for the second component, we have some pretty high loadings here, the 5.3 and the 6.1. Those are telling me that, well, some of these, these components are not particularly unique. They there's a lot of overlap here, and possibly it might not be necessary to have two components. Moving to the next piece here, the H2. H2 is what's called the communality, and that's confusing because there's something there called the com as well. H2 is the communality. The communality, you can think of that like an R-square value. If the factors or components are predictors in multiple regression, which is explaining, in this case, for the first variable, death rate, what we would see is an R-square value of 0.95. And the factor loadings, you can think of those as the standardized coefficients. The standardized coefficient would be negative 0.97 for RC for the first component, RC1, and negative 0.06 for the second one. Just for the record, this is not beer, it's sparkling water. I mean, it's not even noon yet. All right, U2, that's just 1 minus H2, 1 minus the communality. How much is left to be explained? I just deal with these first three columns. Other stuff that we get here. For each component, we get something called SS loading. This is more commonly called an eigenvalue. The eigenvalue is the primary measure of how well a factor explains the variables. One way you can think of that is how many variables out of the total were explained. 2.42, 2.41, those are pretty big values when you consider that we've got only 5 variables in our model. Proportion var, that is what proportion of the total variability is being explained by this component. And you can see 0.48. Where we get that, that's just 2.42 divided by the number of components, which was 5. Similarly, 2.41 divided by 5, about 0.48. Cumulative var, if anything, I'm probably going to present this one along with the eigenvalues. This one will tell me, okay, together the two components explain 97% of the variance in the factors. One thing to note here is 97% of the variance is a lot. You generally don't see that with components analysis, and certainly not with factor analysis. If you're getting around 50% or even mid 40s, you're probably doing a pretty good job. All right, other stuff here, we get mean item complexity. I don't really need any of these other pieces. I don't really use these very much. Oh, fun fact with the eigenvalues. My kids are watching all of the Marvel movies, and I think they were watching one of the Avengers ones, and at some point Tony Stark is doing something where he's being all smart and figuring out some problem, and he says, okay, give me that eigenvalue and this something or other, and I just stopped. I'm like, wow, we're talking about factor analysis in the Avengers. So that's how cool factor analysis is, people. All right, decide how many factors you should use. Again, here I want to make that distinction between factors and components. Get a lot of errors here, or warnings here. Don't stress about that. Well, I would stress about that if these were real data for a real project, but not so much in this case. Here we see with the scree plots. We have our simulated data and we have our actual data. Now you can see it's a lot clearer. When we're using factors, it's very clear that there should be two factors, and 3 and 4 are right at where we would expect to have them with simulated data. And again, parallel analysis will the parallel analysis approach will actually interpret this for you in case it's unclear from the graph. Suggests 2 factors, so we're going to go with 2 factors. I'm going to use, in this case, the FA command, and that comes from the psych package. Number of factors is 2, rotate, varimax as before, and then FM, that's the factor method, PA is principal axis. One thing to note here is that in addition to there being a lot of different approaches to rotation, there's a lot of different approaches to factoring. Principal axis factoring, PA, is probably the most common factor approach, but there's certainly other approaches. Not really necessary to talk about those other approaches, because once you know one of these, all of the others just fall into place. They're all the same, really. We can see with this analysis, we get similar findings. We've got the death stuff on the first factor. We got the life stuff highly loading on the second factor. One piece of information here that highlights some of the differences between components and factors. We can see that H2 values are a bit smaller, especially for death rate. I think death rate was like about 0.98 or 0.99 in the components analysis, but here it's 0.81. The reason for that is because factor analysis doesn't try to explain all the variance. It only explains what death rate, in this case, shares with with any of those 4 other variables. If some part of the variance in death rate is not explained by the others, it doesn't try to explain it. What that means is that we're going to get smaller eigenvalues, smaller total proportion of variance explained. And you can see here we were at 0.94, which is still remarkably high, but it's much lower than it was in the components analysis. Again, thinking about the difference between components and factor analysis, you will see a lot of components analysis in the research literature. Primarily, that is older literature. I think the real gist of this is it was easier to calculate components analyses when people had to do stuff by hand, so that became pretty common. But I think the current thinking is that there's pretty much never any reason to use components analysis. It would be more common to use principal axis factoring all the time. All right, another piece that we'll talk about where talking about how things shifted is in terms of these rotations, so we'll get there in a second. One thing you'll note, the output here, we get a lot of information. I generally don't see many of these things reported, so I'm not going to talk about them in any detail. All right, eigenvalue greater than 1. The eigenvalue greater than 1 strategy, that's a common strategy called the Kaiser criteria. It's not a good strategy because I think it lacks context. You know, if you had a situation where you had 10 variables and you were trying to reduce them into a certain number of dimensions, their eigenvalue of greater than 1, if you think about what an eigenvalue of 1 means there, if you convert that to a proportion of variance, eigenvalue of 1 over 10 variables, that would be 0.10. That factor would be explaining 10% of the total variability. That's not bad. That's probably pretty impressive. Turning that around, thinking about what this would mean if we were talking about a situation where we had 100 variables and an eigenvalue of greater than 1 strategy. Well, there an eigenvalue of 1 would correspond to 1% of explained variance, which isn't really very much. So long story short there, don't use eigenvalue greater than 1, even if you do see people actually using it in the literature. It's not a good strategy. It's not really justifiable. I would always go with the parallel analysis over something arbitrary like this. All right, question 2 asked you to do an oblique rotation. Again, one of the big distinctions between that we make in factor analysis is between orthogonal and oblique rotations. Those are just mathy terms, meaning that the factors are either allowed to be correlated or they're not. An orthogonal rotation uses factors that are completely uncorrelated. So we're putting a constraint on these factors that they have to be completely uncorrelated. That's probably not realistic for most situations where we're talking about psychological scales, which is the primary use for these analyses. You would expect if you had subscales to a general scale, for example, if you had a depression general scale and it had 4 subscales, that the stuff in those subscales would probably be related to some extent. For that reason, oblique rotations are really probably a stronger recommendation now, and you see them more widely used. One thing that's, again, driving the fact that people often used orthogonal rotations is that they were easier to calculate. So, you know, now when we have computers, you know, things take a while to catch up because everybody's looking at older literature and seeing, oh, well, this is how they did it, I'm supposed to do it this way. I think the general belief now is that oblique factors should be the default, and orthogonal you would have to have a strong justification for. All right, so I've done the same analysis with an oblique rotation. Only thing that differs here is I say oblumin here in my rotation. You can see that a lot of the numbers come out the same. That's not always the case. One thing that's a little weird here is that we've got a loading of greater than 1. If you see that in an analysis that you're doing, it should give you pause, and you should say, well, I need to look into this. This is probably problematic. This is really much like, I mean, it's not the same thing, but it's a similar situation that we would have when we didn't center our variables when we're dealing with interactions. We get those wacky regression coefficients. It's the same issue here. It's really just a multicollinearity issue. So that's kind of the issue that we get. We still get eigenvalues. We still get cumulative variance explained. Really, the only thing is that we're allowing the factors to correlate. You can see here the correlation between our two factors was 0.36. Relatively substantial, suggesting, yeah, okay, we definitely do need to let the factors correlate. If this came out to 0, you'd have basically the same as an orthogonal solution. So that's the oblique rotation, not really much additional to it. One thing that's nice about the psych package is that it is taken a lot of the challenges that people used to experience in interpreting factor analyses. Most programs give you 3 different tables of loadings, and you have to know which one to identify. The psych package just gives you the one that you need to do your interpretations, which is nice. Before we go on, just a few things that should be useful on the homework assignment. In terms of reporting and making a table, it'll be useful to have a table that lists on the left-hand side, for each row, the name of the variables. Across the top, the factors. You'd want to give the factor loadings, although sometimes you see in published research, they'll have blanks for certain loadings that are below a certain level. I think a best practice is to have all of the factor loadings. Then I'd have a column for the commonality. You could probably just copy and paste this table, these 3 columns, and then start to apply better formatting to that. So commonality is on the side. Then down at the bottom, below each factor, I would put the sums of square loadings, and the cumulative variance explained might be useful as well. And if the factors are correlated, you might just have a note in your table noting the factor correlations. In the handout, there's a good example of presenting this with a much larger number of variables. But those are, I think, the main things that I would be looking for in presentation. And that would certainly apply to both the homework and the exam, the final exam. All right, so question number 3, just a short one. What's a Haywood case? There were a couple of mentions that R said, warning, Haywood case, Haywood case. Haywood case occurs in factor analysis when the iterative maximum likelihood estimation method converges to unique specific variance values that are less than a prefixed lower bound value. Perfectly clear, right? The big issue here is that everything's so highly correlated that you end up with communalities that are greater than 1, or also factor loadings that are greater than 1. Big issue there is those warnings should tell you, don't trust those solution. If you get those warnings, it probably means that you have 2 variables that are really super highly correlated, so you might think about removing one of those. All right, last question is performing a confirmatory factor analysis on some big 5 personality trait items. And in the assignment, I listed out what the different items were. We're going to do this using Lavon. We've done a lot of work using Lavon, and it also gets used in mediation analysis. Really powerful tool. I think we're lucky to have free tools like this available. It replaces what a lot of commercial packages do. Confirmatory factor analysis, for example, does not come for free in SPSS or some other commercial programs. You need to buy specialized software, and there has been for years a big market in these with programs like Lizral, EQS, and M+, kind of leading, and AMOS as well, leading the way. All of those are expensive, $500–600 for a license. Lavaan is, of course, free and does everything that those packages do, which is wonderful. So the big piece here is building our model. We build the model inside of this statement that has got these apostrophes, or I guess you'd call them. So CFA model, that means it's just going to take everything that's inside of there, and you're just feeding a bunch of equations into something called CFA model, and then you're going to call that over here. You could write these all out in the command down here, but that would be really weird and challenging. So there are 5 factors. So there are proposed to be 5 factors in the Big 5 personality inventory. You probably learned about that in some class, like, I guess, personality, if you took it. Beats me, I don't know. Agreeableness, conscientiousness, extroversion, neuroticism, and openness. Very, very prominent theory of personality. I've taken admittedly a reduced scale here, but 5 items that are supposed to represent agreeableness, and it's these numbers, and those all come from the handout that you're given. So we've got agreeableness, it's got certain values associated with it. Conscientiousness, what this means is the factor is predicted by, or is associated with these 5 values. The factor is associated with these 5 values, and so on down the line for each of the 5 factors. The factors will by default come out correlated, so we don't have to force them to be correlated. That's not always the case, but it is the default in confirmatory factor analysis. Once we've got these equations set up, basically telling Lavaan what variables go with what factor, or what variables are proposed to go with what factor, we give it this this command. You can see we feed it the CFA command, CFA model. Give it the data, and then we use the mimic command. I just like the mimic command because they clearly wrote this to mess with the commercial software. Here they're mimicking M+ and giving you output that looks just like it. And then down below, we want to summarize this. And we're going to summarize it using the summary command. This, interestingly, is a command that is from Lavaan. It's not the general summary command that we use to look at output. So you might actually write this Lavaan : summary, just to make sure that you're getting the right command. If you're getting something that doesn't give you this, that will be the solution. A few statistics that we're going to get here that are useful. There's a lot of output here, a lot of information, and not all of it is really interesting to us. There are a couple of issues with confirmatory factor analysis. One of the first is how well our confirmatory model fits the actual data. That is, we have a theoretical model that there are 5 factors, and those 5 factors are represented by those 5 certain variables. That doesn't necessarily mean it's true. So we're asking, how well do our data conform to that idea that there's 5 factors and each of the factors is comprised of these specific variables? So this is very much kind of more of a theory testing type approach, as opposed to exploratory factor analysis, what we were looking at before, which we're just feeding the data in and saying, okay, what goes with what? Here we're saying these variables go with these factors, period. So now we're asking, okay, that's our belief. These variables go with these factors. Does that actually conform to the data? The first statistic we get is is this thing that's listed as the test statistic. That's more commonly represented as the chi-square. statistics, so it's a chi-square of 433. Important here are the degrees of freedom. In general, these chi-square tests are always going to be significant, which would mean a significant deviation from the proposed model. So here, this test statistic, we generally don't ask, is it significant? We're going to ask, what's the ratio between this chi-square value and its degrees of freedom? Some people say, okay, about a 2-to-1 ratio. That's when you're getting to I should clarify, a 2-to-1 or lower ratio. That's when you're getting good fit. Here we see 433 divided by 265. I don't know what exactly that is, but it's clearly less than 2-to-1. So based on that metric, that we would have good model fit. However, there's not a lot of agreement about these values. You tend to get different situations depending upon the degrees of freedom. The degrees of freedom are an indication of how much you're letting the data be, basically letting the data be free versus how much it's being constrained by specific things that you're telling the data. So 265 is a heck of a lot of degrees of freedom, which means that this value would have to be gigantic to be even more than twice it, so probably not a good indicator here. The p-value here, I would never care about the p-value. People will present the chi-square statistic, but generally they're going to be more interested in some other values. One thing that's important here, don't confuse the baseline model with the user model. The baseline model is a model where we have the data and there are absolutely no constraints put on the data. What I mean by a constraint, every time you say this variable goes with this, these factors correlate with each other, that's a constraint. We're telling we're in our model, we're saying this is what I'm going to fix. This goes with this, rather than there being no restrictions put on the data. Interestingly, if you look at the degrees of freedom, everything that is being estimated eats up a degree of freedom. Every path that's being estimated represents a degree of freedom. That includes these 25 variables. Each of them have a path to a factor, so that's 25. That doesn't get us to the 35 difference between 300 and 265. Where are those other 10 paths coming from? Those are actually the correlations between the factors. If you think about how many correlations there are, you've got factor 1 correlated with 2, factor 1 correlated with 3, factor 1 correlated with 4, and factor 1 correlated with factor 5. As you go through all of those different pieces, I'm sorry, factor 1 correlated with 2, 3, 4, and 5. Then factor 2, its correlation with 3, its correlation with 2, its correlation with 1. Factor 3's correlation with factor 4, factor 3's correlation with factor 5, and then finally factor 4's correlation with factor 5. That's all of the factor correlations, and that's 10. So that's where that difference of 35 comes from, between the full baseline model and then the more restricted user model. All right, I just remembered that from grad school, so I had to tell you. All right, user model versus baseline model. Down below, these are where we start to get into some of the statistics that people will generally rely on. CFI is probably the biggest one here. CFI, comparative fit index. This is a value that ranges from 0 to 1, with 1 being best. In general, most sources would say if you're hitting around 0.95, you've got a model that conforms well to the actual data. Here we're clearly well below 0.95, not even close to 0.95. So that would indicate that we have a poor model. Another value, root mean square error of approximation. In general, people would say, they used to say you want this about 0.05 or below, so here lower is better. Even more restrictive, the entire confidence interval falling below 0.5. Notice that we didn't meet that criteria in either case. If you want to fit in with the stat crowd, never say root mean square error of the approximation. Don't say RMSEA. You have to say RMSE. That's how all the cool stat folks say it. SRMR, standardized root mean square residual. This is another index of how bad the model is, and I'd say, you know, it's again about the same criteria as the RMSE 0.05 being that value. That 0.05 is just coincidentally the 0.05. It has nothing to do with probability of 0.05. So another value saying, oh, we don't have a good fitting model. There's a significance test on the RMSE. I don't like that, so kind of ignore it. Some other indications of why we're having problems with model fit. If you go through and look at the individual coefficients, again, this is how well each variable fits with each factor. One thing you'll always see is by default, the first one is always fixed at 1. That is just how all of these programs do their estimation. They fix one of the paths, which allows it to estimate the others. If we look at some of these, and we can just actually look at the probabilities here, we see, well, question 188, we believe that that was supposed to be part of agreeableness, but it's not even significant here. Similarly, 192, not even significant. When we get down to conscientiousness, we see that none of the variables that we're supposed to associate with it were actually statistically significant. And you see extroversion's doing okay. Neuroticism, those items seem to be related. Openness seems to be, you know, doing okay. But one of the things that this is telling us is that maybe this conscientiousness factor, maybe we need to rethink how that's being measured, because they're not even significant here, which is quite bizarre. So when we see these non-significant paths, that's what's driving that poor model fit. These variables aren't well explained by the factors that we proposed they're part of. Other things here, the covariances, those are interesting in that they are an indication of how strongly the factors correlate with each other. And we can see that although these are all scales on the same, scale, we can see that among these 10 factor correlations, so 4, 3, 2, and 1, among those 10 factor correlations, we only have 1, 2, 3, 4 of them that are statistically significant, and we'd probably expect much stronger relationships between these personality characteristics. So we're not seeing that, suggesting that whatever scale that we're using is not doing a very good job in generating what we would the pattern that we would expect. All right, other stuff you'll see here, the intercepts, don't really need to interpret those. There's a lot of them. You'll see variances as well, a lot of them, don't really need to deal with that. Get a lot of output here. So really important to know what we're looking for. Just to review what we're looking for, these model fit statistics are probably your first place to look. And then these individual, you can think of these as loadings. These individual not factor loadings, these individual loadings are what we would be looking for, particularly if we see some patterns where some weren't significant. That might suggest we put variables on the wrong factor. It might suggest there's a problem with that part of the scale. So those are probably the main places. And then the covariances get at the factor correlations. All right, so in conclusion, does the model fit? No, the Big Five model does not appear, or at least the data that we have do not adhere to the expected, to what was expected by the Big Five model. All right, so just in conclusion, a couple of takeaway points. We've got two main kinds of factor analysis, exploratory and confirmatory. I would say that anytime you have an idea about what the factor structure should be, you should jump right to confirmatory. There was a time where people thought that you would do an exploratory factor analysis, derive 5 factors, and then try to confirm that with the same data. You might do that if you have multiple data sets. explore it in one, confirm a structure in another. But if you have a theoretical reason to believe things are going together, I would go right to confirmatory factor analysis. Another reason why people sometimes would live in exploratory land is because they didn't have the specialized software for confirmatory factor analysis. We no longer have that problem. So I think we'll see confirmatory happening a lot more. Other distinctions that make for great exam questions: the distinction between components and factors, the distinction between eigenvalues and communalities. All of those things are things you should be thinking about as we move toward our final exam. All right, thanks for listening, everybody. I hope everybody's doing well and continuing to socially distance.